Welcome to the second session of the second day of AMERSIE, the School on Advanced Methods for Remote Sensing Information Extraction that is sponsored by IEEE GRSS. And today is my pleasure to introduce you to the speaker of this session. That is, again, an outstanding speaker, and it's a privilege to have him with us. The next speaker is Alejandro Frery. Alejandro, welcome. And Alejandro received a Bachelor of Science degree in Electronic and Electrical Engineering from Universidad de Mendoza, Argentina. His Master of Science degree was in Applied Mathematics and Statistics from the Institute of Pure and Applied Mathematics, or IMPA, in Rio de Janeiro. And his PhD degree was in Applied Computing from the Brazilian National Space Research Center and IMPE. He was the editor-in-chief of the IEEE Geoscience and Remote Sensing Letters during from 2014 to 2018. And currently is the IEEE GRSS Advisory Committee member in charge of plagiarism and future publications. The GRSS granted him the Regional Leader Award in 2018, and he is a distinguished lecturer of the society since 2014. He holds a Huashan Scholar position from the Xidian University for the 2019 to 2021 period. And his research interests are statistical computing and stochastic modeling. He is currently a professor of statistics and data science with the Victoria University of Wellington in New Zealand. And again, really, it's an immense privilege to have him with us here. So I stop sharing my slides and I give the floor right away to Alejandro.
Thank you very much, Andrea. Thank you very much, Salwa. You have organized a wonderful school, and well, I hope this talk will be on par with this fantastic event. So let's start. Just checking. Do you see my slides?
Yes. Yes.
Good. So this afternoon session for you, late morning session for me, is divided in two parts. The first part is about statistical information theory for remote sensing data analysis. And I will focus this part on SAR, synthetic aperture radar image analysis. So let's begin. The outline of this part is I will make a brief introduction to the topic, to the general topic. We will spend some time, a long time, in discussing univariate observations. And by this I mean intensity data, which is probably the most common type of SAR data that users handle. Then we will move into multivariate observations, and by this I mean fully polarimetric data. And I would like to conclude by stating a few research topics, and consider this invitations to perform research. I am very glad that my predecessors, Carlos Lopez Martinez and Avik Bhattacharya, already presented the physical aspects of SAR and then the mathematical challenges and techniques that we use in SAR. Otherwise, I should go back to those topics and come back. So this was fantastic, and thanks to Andrea for organizing things in this way, so each of us can focus on specific topic in this fascinating area. So let's start by a brief introduction. I am very happy not to have to speak about sensors and all that stuff. I will then concentrate on why we need statistics. We need statistics because SAR data are deterministic. Come on, that doesn't make sense. If SAR data are deterministic, we don't need statistics. Okay, SAR data are deterministic, but it is practically impossible to foretell the values unless we have perfect knowledge of the scene, of the sensor, of the sensing conditions, and on the processing change. And this, of course, this perfect knowledge is unfeasible unless we are kind of simulating a sensor. In practice, we don't have such a perfect knowledge. So luckily, and we are very lucky for this, we have excellent tools to perform statistical analysis. By this, I mean that we have careful, detailed models. And by careful and detailed, I mean models that are built from the ground up. So we won't jump to the central limit theorem, although you will see it mentioned, but we will describe in a statistical sense each elementary backscatterer, and we will see how this micro definition becomes a macro observation. So is this worth the effort? Because it's always relevant to think about the effort return balance. Is it worthy studying statistics for SAR? And the answer, in my viewpoint, is yes, a very strong yes. Why? Why is it worth the effort? Because with a careful statistical modeling, we can describe the data. So the first thing that we will see, and I will go very fast in this part, is that when we have the data, we show the histogram and we fit the distributions, they are beautifully fit. If we work with care, the distributions for SAR data describe the data very, very well. But not only that, that is, it's a high when you have statistician side, but that's not the only part. The fun begins with a good description of the data, with a good statistical description of the data. The real fun starts when we propose techniques for instance, noise reduction, for instance, edge detection, classification, segmentation, and many other image analysis techniques based on this careful statistical modeling. In a nutshell, what we do by using statistics is that we are able to extract knowledge from the data. We transform low-level information, numbers, into high-level information. For instance, edges, classes. So it's really worthy learning a little bit about statistics and using statistics correctly. So let's go into the univariate modeling. And remember, by this I mean modeling intensity data. So we have a very beautiful model called the random walk. What does the random walk represent? The random walk represents the complex scattering S, complex scattering. By complex, remember, we mean a real part and an imaginary part. This scattering is what we receive corresponding in the sensor, corresponding to a spot on the ground. We will call this spot on the ground the scene. So this spot on the ground will become a pixel after the whole chain of processing. But what will we obtain up there in the pixel? How do we obtain that number, that digital number? That digital number is the result of the random walk. The electromagnetic wave interacts with each individual scatterer, and each individual scatterer returns a part of the amplitude of the signal, denoted AI, and changes the phase of the signal by a phase difference, denoted phi I. We were saying that this part of this term is the contribution of the ith scatterer to the whole complex signal. And we assume that our spot, the piece of the ground that will become a pixel, this piece of ground has n backscatterers. So we have a coherent sum of n terms. For instance, here we have the return coming from the first backscatterer here. Let me zoom. So we have the return of the first backscatterer here, the second, the third, and so on. So here we have like 15 backscatterers, and the result, what we have at the sensor, is this complex number S. This complex number S is the result of adding coherently the contribution from n backscatterers. Good, nice. So, and here comes our little mathematical beast. The central limit theorem says that if the number of backscatterers is very large, and if the amplitudes of the backscatterers are independent, and the variance of the individual amplitudes is more or less the same. So I don't have any of these backscatterers contributing much more than the others. And if the phases are independent, and if the amplitudes are independent of the phases, and if the phases follow a uniform distribution. So what does it mean in layman's terms? My wavelength is observing elements which are relatively small with respect to the wavelength. And there is no corner reflector or no double bounce in my scene, in what will become a pixel. The double bounce, the no double bounce, the no corner reflector is this condition. This condition says that there is no structure in the amplitude. This condition says that there is no structure in the phases. This condition says that there is no relationship between amplitudes and phases. And this condition says that the phases are essentially irrelevant to my problem. These conditions hold in what we usually call fully developed speckle. In practice, pasture with no relief, crops with no relief again. Those are situations where these conditions typically hold, often over water, but those are physical aspects of the modeling. If these conditions hold, we may say that the intensity, the square of the complex number, of the complex return, the intensity follows an exponential distribution with mean sigma square. Well, this can be proved. In fact, it's a beautiful exercise to prove this, starting from the random walk. Saying that the intensity follows an exponential distribution with mean sigma square is the same as saying that the intensity follows a standard exponential distribution multiplied by the mean backscatter sigma square. Remember this because this will be important in a couple of minutes. Okay, but what happens, and this is what we don't see so often, what happens when the central limit theorem does not hold? What happens, for instance, sorry for, I will reduce the slides. What happens, for instance, when the number of backscatterers, remember that the number is here and we assume this, what happens when the number of backscatterers follows a Poisson distribution? When does it happen? For instance, if you are looking at a forest of grown trees with a resolution of, say, I don't know, 30 meters times 30 meters on the ground, well, what will dominate the return is the trunks, depending on the angle of incidence, depending on the frequency, etc., etc. But let's assume that you are looking at trunks. How many trunks fit in different pixels? Well, a random quantity. We may model such a quantity as a Poisson distribution. But we are totally uncertain about the adequacy of this model. So instead of saying that the number of backscatterers follows a Poisson distribution with a fixed mean lambda, we say that it follows a Poisson distribution with a mean which itself is a random variable. We will say that the mean of the Poisson distribution is a random variable that follows a certain distribution. And this is very general. This distribution can be a constant, and I will have the same Poisson distribution on each pixel. Or this mean can be a gamma distribution. So the Poisson random variable will change from pixel to pixel. And we are saying the random variable, not the observation. The observation changes per se, because these are random variables and these are random variables too. So here we are introducing a lot of variability. This is also called the compound model because we are putting variability in the number of backscatterers n and on the mean of the distribution that models n. Well, by doing this and assuming the same other conditions of independency, we obtain, for instance, among many others, the K distribution and the G0 distribution. We will go into these distributions a little bit later. We will see details about them. The important and the interesting thing is that the K distribution is characterized by two parameters, sigma square and alpha. In this case, we are talking about the single look case. We will see what look is later on. So in this case, we have the mean and a parameter alpha. Alpha is directly related to this, to the distribution of the mean of the Poisson random variable. And we can state more or less the same as we stated for the exponential distribution. We can say that the intensity, which follows a K distribution, is the same as a constant times a standard K distribution with parameter alpha, and we will call alpha the texture. This statistical modeling is so powerful that it is able to connect mathematics, this model, with the ground, with what we see on the ground. How? Alpha is the mean value of backscatterers. So if I am imaging a forest and the K distribution is a good model, and if I estimate alpha, and alpha is, say, 8.5, I know that in mean, in each pixel of the area from which I took the data to estimate the parameter, I have 8.6 trees. So it's a very strong connection between models and the truth. If we make another assumption for the distribution of the mean value of the Poisson distribution, we have an intensity distributed as the G0 model. The G0 model is also a scale model, you see. Again, I can take the mean outside, and I have here the standard G0 model with alpha, and alpha again relates to this in the same way as it was related by the K distribution. The only difference is that alpha is negative. So if I take an area from a forest and my alpha is minus 11.4, I know that in mean, I have 11.4 trees per pixel. So this is a beautiful and not so often seen connection between statistical models and what we have and the nature. What I will mention now is that this scale property that allowed me to take out sigma square from here and from here and from here allows me to formulate the same distributions in a slightly different way. Remember, how did we obtain the exponential, the K, and the G0? Using the random walk model and making n either infinite or a random variable. It's beautiful, it's amazing. The mathematics are fantastic, but it is a little bit tough to work with this approach. By noticing this scale property that I already mentioned, we can obtain the same distributions with another approach. Which approach is it? We can say that the intensity is the product of two independent random variables, x, which models the backscatter, that is the quantity I want to retrieve, times y, which models the speckle, which is the component that I want to get rid of. And this is the formulation that we will use in the following, just for the sake of simplicity. Remember that it is totally analogous to the random walk approach, but we will use this that is called the multiplicative model. And here comes the reason why we call this a multiplicative model, because we multiply two independent quantities, the backscatter. The only thing we assume about the backscatter at this stage is that it is positive, times the speckle that at this stage can be assumed to be an exponential random variable with mean 1. Okay, so I will open the chat. I see a question. Juan Doblas. Hello, Juan. How the compound model hypothesis relates to the wavelength of the sensor? You said that a forest can be modeled with a Poisson model. Yes, it totally depends on the wavelength, on the antenna, on the size, on the virtual size of the antenna, because we are assuming at this stage not very high resolution images, mid-resolution images. And regarding the band, depending on the band is what the sensor will see as a backscatterer. In L band, the backscatterers will be trees. In C band will be something different. In X band will be something different. But I was trying to illustrate with the idea of trees, but it depends on the frequency and it depends on the sensor configuration. Thanks for your question. Okay, so let's move. Remember, we will be using this approach, the multiplicative model. As mentioned, the multiplicative model assumes that the observation at each pixel is the product of two independent random variables, x the backscatter, y the speckle. If we perform multi-look, we will take the average of these observations, and we will assume that x will be constant along this averaging process. So x will behave as a constant for the averaging of the multi-look, and y will be averaged. What is the distribution of the average of L exponential random variables? It's a gamma distribution with shape parameter L. L is the number of looks. We will see this more in detail when we move into polarimetric data. But just remember that in multi-look data, Y has or follows a gamma distribution with mean 1 and L looks, L being the shape parameter. What we want to retrieve X or the properties of X by observing Z. So the first thing that we have to ask is this model correct? That is something that you always have to do when you start working with a statistical model. Is the model correct? And now I quote one of my favorite statistical quotations, which is due to a great statistician. Yes, X should be always positive. This statistician is George Box. And Box said that the most that can be expected from any model is that it can supply a useful approximation to reality. In this sense, all models are wrong. Some models are useful. How come wrong? Yes, because they cannot describe the whole complexity, the whole richness of the phenomenon under study. A model is a summary. A model is a simplified version that hopefully is useful. So our question is not if the model is correct, because if we ask this question, the model is not correct. The question is the model adequate? And I have here an example. In this example, this is a SAR image from Oberpfaffenhofen in Germany. And this is the runway of an airport. And I took a sample of more or less 15,000 observations from this area in yellow. This is a polarimetric image, and I formed the intensity channels. So we have 3 intensity channels. And I showed here the histograms and overlapped to the histograms the densities. Very seldom in practice you see such a good fit of a model that was hypothesized, that was built from hypothesis to the data. And the fit is really, really good. So we can say that the model is adequate and we can work with it comfortably. Let's put these things to work. So our first task is the following. Speckle bothers a lot. Speckle is a problem in some sense. We want to get rid of speckle. And we get rid of speckle by using typically speckle filters. Speckle filters started being researched and proposed and assessed since the early ages of SAR imaging, because speckle is really nuisance. So we have many speckle filters. I suggest reading the paper, beautiful survey paper by Argenti et al. And other authors. And every time we see a new filter, we see that the proposal comes with measures of the filter quality, how good this filter is, because nobody's crazy enough to propose a filter and say, well, have it, here's the filter. Well, the next question is your filter good? So there are ways of measuring the quality of speckle filters. There are almost as many filters as measures of their performance. So we will use the multiplicative model with very mild assumptions to propose a technique for measuring the quality of any speckle filter. And this part is for intensity. So the multiplicative model, remember, is Z by observation is the product of X times Y. X the backscatter, Y speckle. Any speckle filter is an estimator, and now I am using statistical terms. Any speckle filter, denoted by X hat, is an estimator of the backscatter solely based on the observed data Z. So any filter uses as input Z and is an estimator of X based on Z. Simple, isn't it? What would be the ideal filter? The ideal filter or ideal estimator retrieves the quantity, exactly the quantity that I am looking for. The ideal estimator retrieves the backscatter perfectly. The ideal estimator eliminates completely the speckle. So the ideal filter uses Z as input and returns X. So let's now look at the ratio of the observed image to the ideally filtered image. This ratio is Z divided pixel to pixel, pixel-wise, by the ideal filter. But Z is X times Y, and the ideal filter is X. So this ratio image is pure speckle. And what is pure speckle? Pure speckle is a collection of independent, identically distributed gamma samples from the gamma distribution with mean 1 and shape parameter L. So if I have the perfect filter, this ratio image will be pure speckle. Nice. So, but what's the use of this? The use of this is that we can measure, and this is the key word of this talk, measure. We want to measure. The idea is that using this very simple observation, we can measure the distance of an actual filter to the ideal filter. How? We can measure the closeness of the ratio image I obtained with the filter that I am using to the hypothesis that the ratio is a collection of independent, identically distributed observations from gamma 1 random variables, gamma 1L random variables. So we want to measure now the closeness of data to a model, the closeness of observations to a hypothesis. How can we do that? Well, I will give you the references in a moment, but in a couple of papers, we proposed a technique for measuring this distance based on two components. The first component orders first order statistics. Remember, what do we want to obtain? Gamma random variables with mean 1 and shape parameter L. So we measure how close the sample mean is to 1 and how close the sample number of looks, the sample shape parameter, the equivalent number of looks is to the original number of looks. This is what we call the first order component. The second order component checks the independent hypothesis. Because remember, we want to check that the observations come from independent, identically distributed gamma 1L. So, identically distributed gamma 1L is checked with the first order component. The independent part, remember, independent, identically distributed. The independent part is checked with this second order component, which uses Haralick's, one of the Haralick measures of texture and random shuffling. You can go to the paper. It's all explained there. And what we check with the second order component is a measure of the remaining geometrical content. What does it mean? Here we have an example, a simulated example, and that is another fantastic application of this statistical modeling, which is simulation. We can simulate data, as many samples as we want. So we simulated this sample of SAR image in which we have a dark background, a bright foreground, and small pieces of return. We are not requiring central limit theorem or anything, so I can put whatever comes to my mind here. This is my noisy image, my original image, Z, and these are 4 filtered versions of Z. How did we obtain these 4 filtered versions? Well, by using the improved Lie filter, by using the FANS filter, the SRAD, and the PPB. These are very different filters. Some of them, as the Lie, for instance, is fast, SRAD is slow, SRAD is based on a diffusion model, the others use strongly statistical properties, so they're very different. The only thing they have in common is that they are relatively new filters that can be considered state-of-the-art. So I am not putting anything silly here. I'm putting very, very good filters. And these are the filtered images. What do we see in these filtered images? Compare the FANS filtered image and the PPB with Z. What do we see here? The edges of these 2 filters are very sharp when compared to the jaggy, the blurred edges that are retrieved by Lie and SRAD. So in terms of edge preservation, when we look at the foreground against the background, well, we like FANS and we like PPB more than we like Lie and SRAD. But do you notice any difference between FANS and PPB? Look at this missing point and this missing point. PPB killed these 2 strong backscatterers, whereas FANS preserved them. And we want to preserve small details. Okay, let's look now at the ratio images. What is the ratio image? Again, I take Z pixel by pixel and I divide it by, for instance, the Lie filtered image pixel by pixel. And this is what we obtain. These are the ratio images. Notice that the jagged edges became a shadow of the square, both in Lie and in SRAD. Also notice that we can see shadows of the small backscatterers in the SRAD that are not visible or are barely visible in the ELI, the improved LI. Whereas in FANS and in PPB, we don't see anything. So there are traces of remaining structure in both ELI and SRAD. Why? Because they blurred the edges, and this blurring becomes residual structure. Whereas FANS and PPB don't blur the edges, and we don't see any remaining structure. So let's now measure the distance between each of these 4 samples to the ideal model, to the model of independent, identically distributed gamma random variables, and these are the distances. Remember, the further, the worse. The closer, the smaller the distance, the better. So our best filter is FANS. How good was PPB that didn't leave any structure? PPB turns out to be the worst of the force filters. Why? Remember that PPB killed 2 strong backscatterers, so the mean is not preserved there. Whereas SRAD is the second best after FANS, and the next to worst is ELI, just better than PPB. So using this idea, we were able to measure the quality of the speckling filters. Good, Richard, that is what we saw on our PPB. You say that you are seeing this guy. Yes, that guy is barely visible. Okay, so let's formalize this idea. Let's formalize this approach. The rationale, the idea behind the proposal is measuring the distance between 2 objects, 2 very different objects. A theoretical distribution, IID, gamma, 1L random variables, and observed data. And we know how to do this when we perform, for instance, chi-square. We do this when we perform, for instance, Kolmogorov-Smirnov tests. But we did this in an empirical manner, essentially because of the independent component. And this empirical approach, by these 2 components, first order component and second order component, yielded a very good tool, and we published 2 papers about this with MATLAB code. So if you are into running code, you have the references, and with the references comes the code, with which you can measure the quality of a filter. So this is a very important insight. We celebrate this insight. We have performed filter assessment by measuring a distance between data and a model. The general approach will be comparing samples, or samples and models, or models, in order to obtain interesting rules. So now begins the real fun. Let's make a recap. We have proposed a measure of quality of the speckling filters by assuming, and this is very important, what we have assumed so far. We have assumed the multiplicative model for the data. X and Y are independent, X is positive, gamma is 1L. We describe filters as estimators. That was a nice idea. And we compare the ratio image to the properties of pure speckles, so data versus a model. We assume nothing about X. And we need more assumptions in order to proceed. So let's proceed now. So let's obtain the gamma distribution for the return. I mentioned briefly that we apply multi-loop processing to our data in order to improve the signal-to-noise ratio. What is multi-loop processing in a nutshell? It's essentially taking the average over L independent, identically distributed observations. Imagine you have a very high resolution SAR, and you are looking at pasture, for instance, so it's only speckle, and you say, well, I may sacrifice the spatial resolution and take patches of size 2 columns times 3 rows, and with these 6 observations, I will form a new observations by taking the average. Well, you will be performing a multi-loop processing with L equals 6, theoretical L, because they have to be independent, and this hasn't been checked yet, and you took the average. So what happens when we take the average of L independent exponential random variables with mean sigma square? And this is the exponential with mean sigma square was the starting point from the random walk. Remember, random walk plus central limit theorem, we have exponential with mean sigma square. Well, this average follows a gamma distribution with mean sigma square and shape parameter L. The density is this one. We will show densities like this. And something that sometimes confuses people who start working with this is the gamma function, the Euler gamma function given by this integral. But this, the same Greek letter, denotes the gamma distribution with mean sigma square and shape parameter L. So don't confuse them. And we will look at this guy. Well, this distribution, as we saw, is scale invariant, meaning that we can take sigma square out and we will have a standard gamma random variable. Yes, Bhakti, yes, this is the standard approach. Yes, this is what you should do if you want to at least start working with SAR. So let's look at these densities. These are, I hope I won't mess on the screen. These are 3 gamma densities with 1 look, 3 looks, and 8 looks. 1 look is our familiar exponential distribution. When the number of looks increases, the density of the gamma distribution becomes more and more symmetric. But these kind of plots, they are nice for a book, for a thesis, for a presentation, but let's tell the truth, they are not very useful. If we want to extract information from a model, and we are talking about SAR, it's much more convenient to look at the log density or the log scaled density or the semi-logarithmic scale plot of these same curves. This is the semi-logarithmic plot of those densities. This is much more interesting. The exponential distribution that can be used as our baseline is straight line. When I increase the number of looks, the shape changes from a straight line to, well, something which is not a straight line. But the important thing to look at is, take for instance, this point. This is the point 4. How is the probability of observing an observation larger than 4? What happens with this probability when we increase the number of looks? This probability can be visualized as proportional to this area. Remember that these areas are log, but don't worry about that. Well, when I increase the number of looks, the area reduces. So the effect of increasing the number of looks is producing smoother and smoother and smoother images. Why smoother? Because it will be rarer. It will be more and more difficult to observe extreme observations, very bright points, as long as I increase the number of looks. So this is the effect, the probability of observing very large numbers decreases when I increase the number of looks. So that is why I like so much looking at the semi-log scale of the densities, and this is something that we will see along the talk. Okay, but we mentioned, remember the random walk, when the central limit theorem does not hold, when we model the number of backscatterers with a random variable, we obtain a totally different distribution. This distribution, one of these distributions is the K distribution. The K distribution was first obtained by Jakeman and Pusey in 1976, some time ago. How they modeled the mean number of backscatterers as a negative binomial distribution. By doing this, they arrived at this probability density function, in which alpha measures the roughness. Alpha is the mean number of backscatterers, remembering that this is a random quantity. The number of backscatterers is a random quantity. The mean number of backscatterers is alpha. Can you guess when does the K distribution become very close to the result obtained with the central limit theorem? It's not so hard. When alpha goes to infinite. When alpha goes to infinite, we have more or less the conditions of the central limit theorem, and we will see this beautifully in practice. So what do we see in this density? Well, this density has three parameters: the number, the alpha, the texture, lambda, which measures the scale. It has a similar effect as sigma square, and L, the number of looks. We are talking about multi-look observations. And this guy is a Bessel function. You know, Bessel functions, we have several types of Bessel functions, I, J, K. We have complete and incomplete. K is the modified Bessel function of order alpha minus lambda, which is the solution of this integral. We don't have an explicit solution, but we have beautiful numerical functions for this. Let's look at the densities. Well, here we have 4 K densities. Look at this parameter. When alpha is infinite, guess who shows up? The exponential distribution. The exponential distribution is a particular case of the single look, which is this plot, single look K distribution. These 3 densities that start above the exponential are single look intensity K densities with texture 1 point alpha, so very far from the central limit theorem conditions, the gray one. The brown one is alpha equal 3. The almost yellow one is alpha equal 10. We are getting closer to the conditions of the central limit theorem. And alpha infinite in black is, in fact, the central limit theorem. And this guy in black is the exponential distribution, the density of the exponential distribution. But are you sure of that in this plot? No, it's very hard. But if we move to the semi-logarithmic plot, what do we see? Where's my cursor? I lost the cursor. Okay, I'll do my best. Here we have in semi-log scale those four densities. Look at the alpha. Here's the cursor. Look at alpha equal infinite straight line. So that crazy density that depends on the Bessel function converges functionally to the very simple exponential density, to E minus X. That's not trivial result. Well, that's beautiful to try. But what happens with smaller values of alpha? Well, here we have alpha 1.5, 3, etc. Let's see what we have around this value. Use the exponential distribution as a reference, and the area, this area, is the probability of observing very large values. What happens with the other values of alpha when I have less scatterers in mean, when I have texture? This probability increases. So the smaller alpha, the stronger the texture is. The larger the variability is, because I will have a larger probability of large observations. Okay, so this is the K distribution, the single look K distribution. Of course, we have the multi-look case version. So it's all in the papers. I am just focusing on the essentials. But remember, we mentioned another model stemming from the random walk without the central limit theorem. The other model was the G0 return model. Within the multiplicative model, the G0 return results from, as usual, gamma speckle, but now the backscatter is assumed to follow a reciprocal gamma distribution. How about the number of scatterers? The number of scatterers follows a gamma distribution with mean minus alpha. Alpha is a negative quantity to distinguish from the K case. So if the number of my backscatterers is a random variable following a gamma distribution with mean alpha, equivalently, if my backscatter is a reciprocal of gamma and the speckle, as always, is gamma, the return, the result of the product of these two independent random variables follows a G0 model, a G0 distribution whose density is characterized by this expression. This expression depends on alpha, which is negative, minus alpha is the mean number of elements of backscatterers, gamma is scale parameter, and well, L is the number of looks. These parameters describe the texture and scale. We proposed this model more than 20 years ago, and it's still working. How about the densities? Well, again, values far from the central limit theorem and at the central limit theorem, because the previous density converges to the exponential density with L equal 1 and to the gamma distribution with other values of L. So we also have this beautiful convergence relationship, and the larger the value of the texture, for instance, minus 1.5, the more different the density is from the exponential density. But again, it's not so easy to see here. So let's move to the log, semi-log scale. And now we have the exponential in black. This is for extreme heterogeneity, for strong heterogeneity, and for heterogeneity, let's say. So we see again the effect that heterogeneity increases the probability of observing large values. So these models are very powerful. And we have so far 3 models stemming directly from the multiplicative description. Are these models different? Are these models living in different universes? No. These models relate through the random walk description. And also, they are particular cases of a more general distribution, which is called the G law. So Antonio is asking, why modeling X as inverse of gamma instead of a constant? Okay, the real scene does not change, but the number of backscatterers do. Again, imagine you're looking at, for instance, an urban area, and your pixel has on ground size 50 meters times 50 meters. What are the backscatterers in an urban area in almost any frequency? Well, buildings, houses, cars. How many of these backscatterers do you have in this parcel? Is the same as the next parcel? No, it will change. So we will model this change in the number of backscatterers by introducing this extra variability, either in the number of backscatterers, n, in the random walk model, or in x in the multiplicative model. Okay, so that's the reason why. It's beautiful to see the connection of all this distribution with the G law, but the G distribution has been seldom used in practice because it's hard to estimate the parameters. Juan, if you want to consider the density of the backscatters locally constant, if by density you mean the mean, yes, this is what these models do. They consider that the mean number of backscatterers is constant, but the particular number of backscatterers changes from position to position, okay? Otherwise, we are moving from one class to a totally different class, and we are analyzing data from the same class. Advantages and disadvantages of these models. Well, G naught and K are more flexible than the gamma. Why? Clearly, because the gamma is a particular case of both the G naught and the K. So both the G naught and the K have the gamma as a particular case, so they are more flexible. It's evident. The G naught distribution relates to the Fisher-Snedeker distribution, and you all know the Fisher-Snedeker distribution. The Fisher-Snedeker distribution is the name and surname of the F distribution that you use to test the equality of unknown variances for under the Gaussian distribution. That F distribution, well, this is the Fisher-Snedeker distribution, and the G naught is a scaled version of the Fisher-Snedeker. Differently from the K distribution, and now I will focus on the G naught, the G naught distribution does not involve Bessel functions, and this is very good. Although we have very good implementations of Bessel functions, they are numerically a pain there because you cannot index with very large values, and the order cannot be very large, so they are tricky. What is the problem of using the G naught? The G naught has already been called the universal model for intensity SAR data. Of course, we have also a G naught for amplitude. But for univariate observations, the G0 has been called the universal model. So why don't we use it all the time as a rule of the thumb? Because when it comes to estimation, the likelihood function may become flat depending on the true value of the parameters. So, well, if you check the literature that I mentioned, we have a number of papers to escape the trap of the flat likelihood. It's not trivial. It's not terribly difficult, but it is something that you have to take care of. It's not like taking the mean. You have to take care of this problem of flat likelihood. And if you want to use moment estimators, they may not have a solution. Moreover, both maximum likelihood and moment estimators are susceptible to contamination. So that is the downside of using the G0 distribution as a universal model. What can we do? Well, did you notice that the part of filter assessment and this part are very different? We will connect them now. What do we have so far? So far, we have intensity data and a very general model that we want to use, the G0 distribution. What comes next? Well, we have to perform parameter estimation and we want to extract valuable information from the data. But we have the chance of having flat likelihood and we have the chance of having contamination. So how about using this idea of distance to perform estimation? How? Imagine you have data. Data is Z, observations. With these observations, you form a histogram. And then you smooth the histogram. I won't go into details. For instance, with kernels. Why? Because you want something smooth. And then you measure the distance between this fixed object. This object is a function. You measure the distance of this fixed object, the smoothed histogram of your observations, the distance between this to the density of any G0 distribution. Why any? Because theta varies freely. So we can have any G0 density. You measure the distance and you take as estimator the point which makes this distance minimum. Okay. So I will have two curves, one smoothed histogram, the other a density that can be very far from it, and I measure the distance. How? How do I measure the distance between these two quantities? Well, we started thinking about measuring the difference area between the two curves. There are two curves. Okay, so we use the difference in the densities to the square. Okay, but the problem is that if we do this, just this, in practice, we won't use the tails because at the tails, the densities are very small, so their differences are very small. So we kind of scale this by the sum of the densities. And this turns out to be something which is called the triangular distance between two probability density functions, or if you prefer, the triangular distance between two distributions, or it is also called the symmetric chi-square distance. And this works quite well. We have used this in at least 3 papers now. It is very stable, easy to compute, very nice. So what do we do with this? Remember, we want to minimize, in this case, F1 is fixed and we are looking for F2 that minimizes these distances, this distance. How do we look? Well, by moving the parameter theta. Theta in this case, is gamma alpha. What do we have? We have the histogram at the back. I am not showing the smoothed histogram, but imagine a smoothed version of the histogram. And then with a smart algorithm, for instance, the BFGS, standard in optimization, we seek for the pair gamma alpha, which minimizes this expression between the smoothed histogram and a point in the parameter space. And by doing a search, we obtain this red density, and the parameters that index this red density become my estimator. And we call this estimator by minimum distance. Is it good? Very nice, very nice. We obtain very good results even with relatively small samples. And in order to have an intuition about why this is good, imagine that we are using the mean. And imagine that one of the observations is contaminated by multiplying it by 10,000. The mean will change abruptly with this contaminated observation. But imagine now I have only one observation, as previously, contaminated by 10,000. What will change about the histogram? Only one beam, and a beam that is far away from the body of my histogram. So that is the geometrical reason why these minimum distance estimators perform so well when the data are contaminated. But remember, we have used the triangular distance. Are there other distances? Yes. We also chose the triangular distance because, well, it's numerically stable and it belongs to a family of divergences. Remember Kullback-Leibler divergence? It's a member of this family. The triangular distance is a member of divergences between distributions of the same type. This family of divergences is called H-phi divergences. The H-phi divergence between two members of the same distribution indexed by different parameters, as was the case of our search for the parameter that was closest to our data, the H-phi divergence is the result of computing this. I take the ratio of two densities, this is a function. I transform this function by phi, a convex function, and this becomes a new function. And now I integrate this new function with respect to the second density, and this is a number, and I transform the number by the function h, which is strictly increasing. So with the conditions that h is strictly increasing and takes value 0 at 0, and phi is convex, and I only have to require first derivative for h and first and second derivative for phi, only that. Imagine the freedom you have. You define the family of H-phi divergences. But divergences are not necessarily distances. The triangular is. But for instance, the Kullback-Leibler divergence is not a distance. How do we transform a divergence into a distance? Well, very simple. We take the average of the H-phi divergence between model 1 and model 2, and the same H-phi between model 2 and model 1. This average is a distance, and this will be fundamental in the rest of our talk. So, besides having a very general setup, what do we have? Well, by choosing h and phi, we have the Bhattacharya distance, the Renyi distance, the triangular distance, the harmonic distance, the chi-square distance, the Kullback-Leibler distance, the Hellinger, my favorite, distance, the Habda-Sharbat distance, the Sharma-Mittal distance, and many, many, many other distances. In fact, you may propose your own functions, h and phi. Okay, so we were saying that this h-phi divergence approach gives us a very beautiful, very comprehensive mathematical umbrella. The first question that we should ask in such situation is, can we make it different? Is there any other relevant approach for measuring distances? And why do we ask this question? Because notice that these h-phi distances measure the distance between two objects. What happens if I want to measure distances between three or more objects? Of course, I can compose them, but is there any direct way of doing this? Yes, the answer is yes. So let me add another piece of theory to this discussion by presenting another family of distances. This family of distances is mathematically a little bit more, say, complicated. I don't like the word complicated because they are complicated for me. For many other people, they are not complicated. But these distances, this other family of distances, relies on solving this equation. Look at this equation. This equation is a double sum of partial derivatives with respect to the parameters. So if I have one parameter, one term. If I have two parameters, well, two terms, and so on. And the crossed terms. You have two parameters, three terms. What do I sum? I sum the minus, no problem, expected value of the second derivative of the log of the density with respect to the parameters. What is this? Well, my friends, this is the Shannon entropy. This is the ij entry of the information matrix of the model D. So what is this doing? This is connecting the idea of distance to immediately the idea of information, the information matrix. The little problem, the small problem, which is not so small, is that in order to this quantity to have good properties, the integral should be performed over a geodesic. And geodesics are not so easy to obtain. Okay, well, and this is a distance. Yes, this is also a distance. This is called the Shannon geodesic distance. In the same way that this is the information matrix, the entry of the information matrix, and this connects with the Shannon entropy, we can define generalized entropies similarly to the h-phi divergences in the same way. So we will define a generalized entropy, the h-phi entropy, as this function. Again, phi is convex, h is increasing, and we will call this the h-phi geodesic distance when we plug this here. These things are usually tough to obtain, but in some cases, they are very easy to obtain, and they have very good properties. Which properties? We will see in the following. What do we have up to this point? Well, we have shown evidence by two examples that the distance between data and a model produces interesting results. An interesting measure of the quality of a filter and an interesting estimator. Okay, but we have mentioned that we can plug different forms of distances. For instance, I plugged the triangular distance. What if I plug the geodesic distance based on the Shannon entropy? Are these quantities comparable? No. Do these quantities tell me if I am close or far? No. They are just measures without scale. They are measures without semantic meaning. As such, there is not such a notion of close and far, and we cannot compare them yet. Now it becomes really fun. Take any h-phi distance, any. Hellinger, Bhattacharya, triangular, whatever, Hellinger, whatever, Kullback-Leibler. Index the distance, not by the parameters now, but by the maximum likelihood estimators of the parameters. These maximum likelihood estimators are based on samples of size n1 and n2, and scale the distance by this factor. This factor depends on n1 and n2, and depends on the first derivative of h at 0 and the second derivative of 5 at 1. What do we know about this quantity? This quantity asymptotically follows a chi-square distribution with p degrees of freedom, in which p is the size of the parameter space. So if we are comparing two exponentials, p is 1. If we are comparing two normals, p is 2. If we are comparing to G0 or K, P is 3, and so on. It's the size of the parameter space, the dimension. Wow. And this holds for any H and any phi. So this quantity that we may call now S for test statistic, S H phi, sorry for the crappy handwriting, these quantities now are comparable, because regardless H and phi, they converge to the same distribution. Moreover, and more importantly, since they converge to this distribution when the parameters are equal, this is a test statistic for this null hypothesis, and it has no asymptotic distribution. We moved from measuring in scales that are different, that are not comparable, and that have no semantic meaning, with a very simple scaling. Look at this. This is really, really simple. We moved from something which was totally abstract into something which is totally useful, because now we can compare these things and we can use these things as test statistics. Well, the same we can say about distances based on generalized entropies, with a big difference. The test statistic for generalized entropies has this form, and we can sum over these quantities and obtain a test statistic for not only two samples, but for several samples. And this quantity also converges in distribution to a chi-square random variable. So we have comparable things regardless our choices of H and phi. So we can plug in any entropy. Oh, sorry, the question and answer was closed. The slides are, the references are at the end, okay? Okay, yes, at the end there are all the references. So Wonderful. We have a plethora of test statistics. So what can we do? What do we know up to this point? We have test statistics based on information theory, divergences. Each A-phi divergence can be turned into a test statistic, and we also use entropies. Each H-phi entropy can be turned also into a test statistic. And we have test statistics based on information geometry. Remember that we could switch the Shannon entropy for other entropies, but we always have to walk through a geodesic. So we call this information geometry based. All these test statistics have known asymptotic distribution. So they are interpretable and they are comparable. Moreover, for these distributions that we use in SAR, they are very well behaved. They work quite well even with very small samples. By very small, we will see an example in which the sample size is 4. And we can use the asymptotic results. So amazing tools, amazing tools. What time is it? I totally lost track. Yeah, 1 hour 30. Let's see examples, and then we go to a break. How can we make this? How can we turn this into tools, practical tools? We want to tell the user, throw your data here, call this function with your data, and I will return something useful for you. For instance, edge detection. We want to detect the edge over a very fine strip of data, very fine, very thin strip of data. I made a thick strip to be able to see it. Visually, we see that the edge is here. How can we detect it? Well, there is something called the Gambini algorithm that proposes the following. Go step by step, and at each step, take the sample to the left of your cursor and compute the statistical properties of this data. Then take the sample to the right and compute the statistical properties, measure the distance. Then go to the next step, compute the statistical properties and the statistical properties, and check the distance of the properties of the distributions. You go, at some point you are here. In all these cases, when our cursor is in these positions, what happens? What happens, for instance, at this position? We will take this sample, we will compute the statistical properties of all those data, and we will take this sample, and we will compute the statistical properties. What happens with the sample to the right? It is mixed. It's like coffee and milk. It is mixed, whereas the sample to the left is pure coffee. What happens when I am at the edge? At the edge, I have only coffee to the left and only milk to the right. So the samples are pure. The statistical properties will be very different. The distance between the models will be maximized. That is the idea. Let's see if it works. It works beautifully. It works beautifully. Look, in this plot, we show the geodesic distance, we show the triangular distance, and all the distances in a variety of situations detect the edge. Does it work? Can it be used? This is an actual SAR image. Very good question, Richard. I will ask after this. Let's take a piece around this area. Here's the zoom. And now, differently from Sobel, Canny, and whichever low-pass filter, instead of using local measures, we will use only 1 pixel width string. So I will go line by line, and I will detect the edge. So in the first line, I detected this red point. In the second line, this one. Third, this one. Fourth, this one. I detect one evidence, one piece of evidence per line. I am not using the neighboring lines, the neighboring, lines. I am using just the line. This is the difference between this approach and Sobel, Canny, etc. This approach will produce one evidence per line. And what happens if there is no edge? We are using statistical tests. So the statistical test will tell me there is no evidence of change. And I will not put a point. And after I do this, I can join the points with a spline or whatever. And this works in the paper, Richard. You can check that we compared with Sobel, Canny, and the TUSI edge detectors, and this technique is much, much better under heavy noise, as this case, speckle. So we are using distances to provide evidence of edges from low level to high level information. And it's a good moment to stop before we go into polarimetric setup into multivariate observations. So now we move into, as announced, multivariate observations. How do we obtain multivariate observations? We will be modeling pulsar data. The random walk still holds. That's a beautiful part. We have the same random walk model, but we have a random walk for each polarization. And if the target can be seen as textureless, so we have infinitely many backscatterers and all the other conditions. And if the medium is reciprocal, so we can discard the VH component, the target will be characterized by this vector, by the scattering vector, that has three complex entries. Each of these entries, remember from the random walk, each of these entries is complex. And under these assumptions, each of these entries follows a zero mean complex Gaussian distribution. Collectively, the three complex elements follow a zero mean complex Gaussian distribution. What's the difference between a multivariate Gaussian distribution? Well, it's not very difficult to move from the usual multivariate into the complex multivariate. It's just a matter of adjusting the covariance matrix. Okay, so this is our complex scattering from a single pixel. We now perform multi-look in a different way. We take the average over L ideally independent, identically distributed random matrices or random vectors, but we multiply S by the transpose conjugate of S. So each of these terms is now a matrix. And we average L of these matrices. With this type of multi-loop processing, our observation, our polarimetric observation, has the form of this matrix in which the diagonal is formed by the intensities. The intensity in the HH channel the intensity in the HV channel and the intensity in the VV channel. These are real numbers. Off diagonal are complex numbers. The covariance between the HH and HV channel, the covariance of the HH and VV channel, and so on. This is in the upper part, in the upper diagonal part. In the lower diagonal part, we have the same elements, only that they're conjugated. So a trick, if you want to store fully polarimetric data, you only need to store this part, because this part is obtained from the other one. So in fact, we only need to store 3 real numbers plus 3 complex numbers. So 6 values plus 3 values, 9 values. 9 values characterize the complex, fully polarimetric observation. Franco, at the end of the talk, you will have huge amount of references, and if you want to discuss, I will be open to answer questions by email. So this is our multi-loop polarimetric observation. It's a matrix. In each pixel, we have a matrix. How we store it is a totally different question. But in principle, the random variable at each pixel is a random variable whose outcomes are complex matrices. We need a distribution for this guy, a distribution for complex matrices. Complex matrices which are, moreover, positive, definite, Hermitian. Do we have that? We have a fundamental result due to Goodman. Goodman worked for optical polarimetry that was already mentioned by Professor Avik Bhattacharya. Goodman in 1963, from a purely theoretical viewpoint, obtained the distribution of Z, the distribution of this complex Hermitian positive definite matrix under the zero mean complex Gaussian distribution. The distribution of Z is called the Wishart, the complex Wishart distribution. The complex Wishart distribution is the analogous for polarimetric data to our gamma distribution. It's the counterpart. And we will see if these two distributions have a close relationship. The complex Wishart distribution is characterized by this density, and I always tell my students, whenever you are faced to a new density, to a new probability model, which is characterized by a density, look at its kernel. Forget about the details. Look at the parts that depend on the argument Z. So what do we have here? We have a density that depends on Z to the L minus P, that sounds familiar, times E2 minus a number times Z. It looks like the gamma. In fact, this, the Wishart, and this, the gamma, they are very close. Only that the gamma is univariate, and this is multivariate in the sense that Z is any positive definite Hermitian complex matrix, and P is the dimension. In all the cases that we will see, P equals 3, because we will be modeling HH, HV, and VV in a single frequency. But if we have more frequencies, we can add dimensions to P. Well, the basic property of this Wishart distribution is that it is indexed by 2 parameters. Its expected mean that no longer is sigma squared, but sigma, capital sigma. You see, that's the idea of matching the parameter names. Here it is sigma squared, and here it is capital sigma. Here it is a number, and here is a matrix. And the distribution is indexed by a matrix of values and by the number of looks. The number of looks is the same. It's the result of multi-look processing. In what follows, we will assume L known, but you can estimate it locally. There are many papers about it. For instance, this nice paper by Sen and other authors. Well, we were talking about tests. We were talking about the SH5, remember, based on divergences. We mentioned tests based on entropies, and we also mentioned tests based on geodesic distances. Can we do this for this distribution? We mentioned this when we were talking about intensity data. Can we do this for polarimetric data? Yes. If we assume the Wishart distribution, we obtained, 2014, several of these tests under the Wishart model. Several, the Bhattacharya, the Hellinger, the Kullback-Leibler, Renyi, triangular, several of them. And this paper has all the expressions in all particular cases. The surprising, the striking fact is that these tests have relatively simple expressions. In particular, they rely only on the determinant and on the inverse of the parameter. Remember, the parameter is a matrix, a complex matrix. Moreover, in this paper, we show that you can implement the computation of the determinant and of the inverse in a fast way. So don't worry about the computing time. It can be done fast. And also, as I mentioned earlier, these tests have very good finite sample performance. You can assume the asymptotic distribution even with samples as small as 4. So if you have 4 pixels, you compute any, not any, but the most usual SH5 test statistics, they will behave as a chi-square distribution. Fantastic properties. Do you remember that we found edges on intensity data? Well, we also found edges with Wishart distribution for polarimetric data. And here I am showing you the results of applying the Kullback-Leibler, the Renyi with one exponent, Renyi with other exponent, the Hellinger, the Bhattacharya, and the maximum likelihood edges. You see, we draw a ray and we find the point at which the distance of the model which characterizes this sample and the model which characterizes this sample, this distance is maximum. Which distance? In this case, the Renyi. Do these edges, are these edges equal? No. They are comparable because we are using test statistics, but they are different because each test statistic looks at a different feature. We have had a paper accepted, just accepted, it's in early access, where we propose techniques for fusing these pieces of evidence. Okay, so we compute these distances and then we fuse the evidences to obtain a better estimate of the edge. So the same idea can be used, just changing the model. Very nice. Pulsar data have a problem. Look at these two urban areas over Mumbai. They are relatively similar. They're very similar, in fact. But when we go into the pulsar image, this area looks green in the Pauli decomposition, and this area looks pink. Pink is typical of urban areas, while green is typical of area with volume backscattering, forests. So why does my sensor see this area as forest when this area is urban the same way as this area? Why? Why is it happening? This is the problem of the alignment, how the urban area is aligned with respect to the line of sight of the sensor. When the line of sight changes with respect to the orientation of the urban area, we may have this effect, and we don't like this. We are very unhappy with this. Let's look at another example. This is a forest area, tall vegetation area. This is a photo, the Google Map photo. In the polarimetric image, Pauli decomposition, this area and this area look very similar. But this red area is urban, totally different. So in the previous example, similar areas look different. And in this example, different areas look alike. We don't like this. And this is again the effect of the orientation of the target, of the urban target, with respect to the line of sight. How can we alleviate this? Professor Avik Bhattacharya made a brilliant presentation of decomposition and factorization. In this line of thought, and Professor Avik mentioned, we have decomposition techniques that for each pixel tell us which is the amount of volume, say forest, surface, say bare soil, and double bounce, say urban area. In lay terms, those are the double bounce, volume, and surface. That's the interpretation of these three types of scattering. We have this San Francisco image, and here we have the areas A, B, and C. A is urban, not aligned with the line of sight. C is strong double bounce, and B is vegetation, tall vegetation. And this is the decomposition as obtained from the original image, from the image transformed by the Yamaguchi four-component decomposition, and by a new kind of decomposition. But let's compare these two, the original versus Yamaguchi 2. And we are interested mostly in area A. This is area A. So what do we see? In the original image, this part that should be double bounce, should be red, is mostly volume, mostly green. Red, double bounce, is only 2%. When we apply the Yamaguchi four-component decomposition, we go from 2 to 3%. Okay, it improved, but not as much as we would have liked. Well, areas B, tall vegetation, and C, double bounce, this is the Golden Gate Bridge. Well, you see C in the original data is predominantly double bounce. Yes? It's like a huge corner reflector. And also it is a huge corner reflector in the Yamaguchi four-component decomposition. So it works well, the decomposition works well over a corner reflector, a huge corner reflector, metal bridge. And how about vegetation? Vegetation, which is a volume scattering, green, Well, it's 69 in the original data, 67 in the Yamaguchi four-component decomposition data. Okay, it works well. Our problem is here. Our problem is that the Yamaguchi four-component decomposition is unable to extract the urban area, the double bounds. So what did we do? We thought, well, what do we want to perform? If this is the original data, we want a transformation that changes the original data in such a way that it does not alter the power, and that we have positive powers in the decomposition, and in such a way that over urban areas, regardless their orientation, this decomposition extracts more information. We achieve this by maximizing the Hellinger distance between the original data and the transformed data. And well, this is the result. You see that the case that was bothering us, this 2% that Yamaguchi raised to 3%, now goes from 2% to 17%. So more than 8 times the original amount of double bounds. And this was obtained by maximizing a stochastic distance between the original data and the transformed data. Not any transformation, but rotations. Why rotations? Because they preserve energy and all the mathematics work. This technique, we are very proud, was incorporated into the latest version of ESA's Pulsar Pro. And well, the developers of Pulsar Pro called it the Bhattacharya and Frery decomposition. I don't know if Avik is listening to us, but we are very proud of this. We are very proud of seeing our paper assimilated by the Pulsar Pro, which is kind of standard platform for processing polarimetric images. Okay, what else can we do? We can perform filtering. What's the relationship between distances and filters? One of the latest approaches for speckle reduction, for noise reduction in general, is called the non-local means. Why non-local? Because we use huge windows. Instead of a local window of, say, 3 times 3, 7 times 7, we use windows of size 21 times 21 or even bigger. Why means? Because we will form a convolution mask for this huge window, and we will apply it. And a convolution is a weighted mean. So how do we obtain the weight W1 for this position? This is my convolution. This is the convolution mask. And I will convolve the original image, Z, times, not times, I will make a convolution of Z with this mask. So I have to put a weight on each position of this mask that has dimensions, say 21 times 21. How do I compute this weight? Okay. What do we want? If the observations, this weight corresponds to this position. How do we compute a sensible weight for a convolution? If the observations are similar, the weight will be high. If the observations are different, the weight will be low, because we don't want, for instance, to blur edges. If I have an edge here, this observation will be very different from this, and I don't want to use this observation. So I want to put something that is close to 0 in this coordinate of my convolution mask. So we want to measure similarity. We know how to do that. We know how to do better than that. What do we know to do? I will take a sample around the central pixel. Let's denote it by this red mark. And I will use this sample that consists of, for instance, 9 observations to compute an estimate of the parameter of the distribution D. I didn't mention it, but we need a distribution, any distribution. For instance, the Wishart distribution, whatever you want. So the Wishart distribution that is characterized by the covariance matrix sigma and the number of looks L. So I use these observations and compute the estimate theta 0 hat. I leave it there. And I compute with these observations around this position, these observations, which now are 25, I can choose anything. I compute the other parameter theta 1. And now I compare the models D indexed by theta 1 hat and theta 0 hat by means of a distance. And since I have a statistical test, I have a simple transformation that turns this into a statistical test, I can obtain a p-value. The larger the p-value, the higher the evidence that the samples come from the same distribution. So the larger will be W1. So I transform 2 patches of data into 2 parameters. I compare them by stochastic distance. I transform this into a test statistic. I obtain a p-value, and I can transform the p-value into a weight. And I do this for every pixel in my search window. In the case of this pixel will become W2. In order to compute W2, I use this sample that can be any size. Notice that here I use a sample of size 25. Here I use a sample of size 9, just for the sake of generality. And with this sample, I compute theta 2, then I compare theta 0 with theta 2, I obtain a distance, a test statistic, a p-value, and the p-value becomes a weight. By doing this, I form a convolution matrix for this pixel. It is expensive, but I would say that non-local means are state of the art. And once I compute the convolution matrix, I apply it. How? It's a weighted average. The weights are these W's. What do we obtain by doing this? Assume the Wishart model. We estimate the covariance matrix, the number of looks, and then we use a distance between Wishart distributions. We obtain the test statistic, the p-value, and the weight. This is the original image. Look at the speckle over the C, it is evident. And this is the result of applying one of the filters available in Pulsar Pro, which is the boxcar. Boxcar is just the mean, where all the weights are equal, 1, say. In fact, it reduces speckle, but it destroys also information. Look at that, we cannot really see the urban structure. It has vanished. If we apply the non-local means using the Hellinger distance, we obtain this image in which speckle has been reduced, but we also preserve fine details. This area is a golf course. Look at that, we still see paths, and look at the beautiful urban structure that has been preserved. How did we do this? By computing stochastic distances between Wishart models. And we turned these distances into weights of a non-local means filter. It works beautifully. It's a paper. But visual inspection is always tricky. That is why, remember the first application, we will look for measures or other types of assessment. One of the things that we want of a speckle filter for polarimetric data is that it preserves the signature, the polarimetric signature. And Professor Abik also mentioned the alpha H plane, the alpha H visualization. This is the original data in which we plotted 3 different samples from different areas in blue, pink, and red. I don't remember which are they. And this is the result of those areas. After boxcar, you see that the blue is more clustered, more concentrated. That is good. The pink has been really concentrated, and the red has been also concentrated and taken into this distinct type of scattering. And what happens when we apply the Hellinger filter? We obtain this. Clusters even better. So we don't lose detail and we don't lose the signature. These filters have this beautiful property. They are very, very good. They are very good at combating speckle, at not destroying details, and they also preserve the spectral, the signature. They also preserve the signature, and they make the observations more distinguishable, at least in this H alpha plane. So what did we do? We reduced speckle by non-local means using distances. A very basic way of segmenting SAR images, and this is done by many practitioners, is the following. Practitioners take a polarimetric image, they apply an over-segmentation technique based, for instance, on the Gaussian distribution. I know it's crazy, but it is practice. It is done in practice. And they obtain lots of segments, but many of these segments belong to the same class, and they should be grouped. They should be classified. So we started by this pipeline, which is common practice. This is done by an algorithm that assumes Gaussian distribution. Not adequate, but it works. We have an over-segmentation. And we said, well, since we have small segments, let's do the following. Let's take prototypes of classes that we know are there. For instance, this yellow is one type of crop, this light blue is another type of crop, dark blue is river, and so on. So we form models. We form the model D1, distribution number 1, the model D2, distribution number 2, with the prototypes. And now we go segment by segment. There are many segments, but we go one by one and compute the distance of the segment to all the models. And we classify the segment to the distribution which is closest. Closest in which sense? Well, we have many ways of measuring distances between samples and distributions. And also we can assess the significance of this measure. And we obtain very good results like this. Look, for instance, at the river. The river is just perfectly classified. And this is just one of the examples. We use in the paper many distances to perform this classification. So what can we do with distances? We can classify segments by minimum distance. Very nice. So remember that when we spoke about entropies, I mentioned that entropies were useful at comparing more points, not only 2 pair of points. Well, we did this in order, but only with a pair of pulsar images of the same area in different dates. We had 2 dates and we obtained fantastic results. This is the pulsar image, Pauli decomposition. Date 1, this is the pulsar image, Pauli decomposition, over the same area, date 2, and you see this has become urban. In fact, it was prepared to build. And there are many other changes. Our user provided this binary map of change, in which black denotes change and white no change. What we did here, we compare very small samples, 2 times 2, in this image with the corresponding 2 times 2 sample in the other image. We took these samples, computed the entropies, entered into the test statistic based on entropies, and obtained a p-value. And this is the map of p-values. So we don't have a binary image. We have a continuous, an image of continuous variation of evidence of change. Well, here it is inverted. In black, no change. In red, strong evidence, and small spots of, you see, green, yellow, blue, green, intermediate evidence of change. This technique performs, at least in this data set, better than the Conrad-Sen change detector based on the ratio of likelihoods. What did we do? Change detection. Based on what? Distances between entropies. So there seems to be a question. Somebody raised the hand? No? Okay, I go on. So we have a change detector, and this change detector can be used in multi-temporal data because the test statistic based on entropies admits 2, 3, any number of instances, any number of epochs. Nice. What else can we do? We have to stop a little bit now and think and ask ourselves a question. Are multivariate and univariate so different? Yes and no. They are different because they describe different objects. Multivariate describes complex matrices. Univariate describe positive observations in the case of intensity SAR. But the Wishart, in this sense, the Wishart distribution for polarimetric includes as a marginal model the gamma distribution. So they are not different. The Wishart distribution is a multivariate generalization of what we saw at the beginning. But at the beginning, we saw the gamma, and we also saw the K, and we also saw the G naught. Do we have such generalizations for polarimetric data? Yes. We have polarimetric versions of the K and polarimetric version of the G naught distribution and of many other distributions. And all of them reduce to their respective marginal distribution. For instance, the polarimetric G naught becomes the intensity G naught when we take the marginal of one of the diagonal elements. So what's the message of this slide? Do not think that we are working with like a box of tools. This is a hammer and this is a screwdriver and this is a chisel. No, we have a very general tool that becomes multivariate when I want it to become, becomes univariate when I want it to become univariate. So it's important to have this unified viewpoint because in a sense, everything reduces to working in a smart way, knowing that at some point in your life, you will probably have to work with polarimetric data. So similarly to what we have for intensity data, there are many other models, and you have an excellent reference by Deng and other authors. One of the other authors is Carlos Lopez Martinez. So I really recommend this paper. This is a very, very good paper. And we are reaching to the end of this talk. We will move to the other part with some research topics because most of the audience is comprised of students. And of course, I want to seduce students to work with this area, maybe with me. There are many, many topics, many research topics. For instance, and I have only mentioned those that I am thinking most of the time. How can we devise very resistant estimators? By very resistant, estimators that perform well with small samples and that perform well when there is contamination. Well, we know a very resistant estimator, the number 42. There is no contamination that affects the number 42, but we also want efficiency. We also want the estimator to give us a good estimate, okay? So it's resistance and efficiency. We want estimators which are at the same time efficient and resistant to contamination and to small samples. There are infinitely many stochastic distances. As far as I know, and my research, the research team in which I participate, as far as we know, only a few have been tested. But we know results from other applications, for instance, in tomography, where the distribution is Poisson, they have used the Havda-Sharvat distance with success. So there's room for infinitely many equations, new equations, when we take other distances, other entropies, and put them to work for SAR. New change detectors. Every time we come up with a new distance, we have a new non-local mean filters, we have a new change detector, we have a new classificator by minimum distance. In particular, new change detectors they rely critically on good estimators. So new change detectors that perform well under contamination and with very small samples. New filters. As I mentioned, the non-local approach is open to infinitely many variations. Theoretical properties of these distances and tests when we don't use maximum likelihood estimators, I mentioned very briefly that these test statistics have known asymptotic distribution when we use maximum likelihood. What happens if we don't use maximum likelihood? What happens if we use moments, log moments? If we use robust estimators? We don't know anything. We have evidence that they perform well, but which are the theoretical properties? We don't know. PhD thesis. The distribution of the composition components. Remember, Yamaguchi 4 components. What is the distribution of each component? We don't know. And that's beautiful research topic. And for me, the most beautiful one, I am currently working on this, is on the distribution of features from the Keno representation. You saw the Keno representation with Professor Avik. Purity, helicity, and scattering type alpha, a scattering type angle. What's the distribution of these guys? We have partial evidence, we have empirical evidence that the scattering type angle follows, overcrops, beta distributions. Why? Can we obtain this from a theoretical viewpoint? And what happens with the helicity, which is the product of two of these distances? Beautiful, beautiful research topic. These are only a few research topics that I wanted to mention. And well, I am concluding with this. This is my contact. And whatever you need, the slides, I don't know if Andrea already received them. The slides conclude with a fairly good amount of references, all dealing with these topics. So, questions, comments after you say what you want. We will make a very short break before going into the next session. No questions? How many are there? 71? Juan.
There is
okay,
one.
Juan. Yes? I don't see the questions. Do you see the question, Andrea?
No, I think I guess that Juan is typing, I guess.
Okay, of course. Andrea, did you receive the slides?
Yeah, I have them, and I mean, we will have to bring all the material together in the next few days, and as soon as we have a proper repository, we will then distribute with all the participants. And of course, we will keep everybody updated with the emails as we did so far in these days. I don't know. Actually, I don't know if Juan is. I mean, we are still waiting for.
In any case, Juan, you can send me your question by email. Okay. So how, I don't know, here, the stochastic distance filter Torres uses a gamma distribution. No, it uses the Wishart distribution. Probably you're referring to the paper we published in IGRS. We have a paper in pattern recognition where we use the Wishart, the fully Wishart distribution. Will it be possible to create a filter for, let's say, a wall? What's behind the wall? Richard, I have no experience with through the wall imaging, no experience at all. We may discuss. I love to see data. Thanks a lot, Andre. Okay. So how about 5 minutes? Nice introduction. I am wondering to know about the nature of the distribution while multiple distances are supposed to be mixed. I would like to have your question in detail by email, Jasser. I'd like to know if using a gamma distribution for intensity instead of G is too adventurous. You're very tricky, Juan. Yes, we do this. We do this with a trick. You can do this if you estimate the number of loops, because when you allow the number of loops to vary, if you fit a gamma model over extremely heterogeneous data, you won't have a perfect fit, but the number of loops will reduce and you have a better fit than the one you would have with a gamma distribution with fixed number of loops. Yes, it's a trick. And I have to confess, we use this trick every now and then. Very good question. 5 minutes? Yes, Juan. Yes, those estimates should be local. But we don't do this all the time. We have a compromise between time, variability, and the result. It depends on what you want to obtain.